In this lecture, we're going to introduce the idea of Lagrangian relaxation. Lagrangian relaxation builds on the thing that we talked about previously, which is dropping constraints out of an integer program. So for example, if we have the integer program pictured here, and we simply cross out this constraint, this results in some upper bound. Unfortunately, by dropping this constraint, it's sort of a silly thing to do, and Lagrangian relaxation is going to have a better way of dropping constraints out of an integer program. The actual procedure to take a Lagrangian relaxation is quite simple, but in order to use it effectively, we have to understand where it's coming from. Let's just build some notation. We'll call the feasible region of our integer program x, and we'll call its objective function f of x. To take the Lagrangian relaxation, the first thing we're going to do is identify the constraint we'd like to relax, in this case the sum of kixi is less than or equal to L, and multiply it by some number, lambda. And this number, lambda, for now is going to be a constant. So we'll take a note of that. It's going to be some constant. And now we're going to make a few observations. The first is that in any feasible solution to our integer program, the constraint that we're relaxing is going to be satisfied. As the sum of kixi is going to be less than or equal to L. And as a result, the sum over I of kixi minus L is going to be some quantity that's less than or equal to 0. Now if I take this constraint and I multiply it by lambda, the sum over all I of kixi minus L, this is still going to be less than or equal to 0 for all lambda that are greater than or equal to 0. That is, I didn't change the sign of this operation. And this is true for all x in my feasible region. So for any feasible x, this constraint is going to be satisfied. So the sum of the kixi minus L is going to be less than or equal to 0. And so if I multiply it by any multiplier that's greater than 0, it's going to remain true. What's important now is that if I were to consider this quantity, lambda times the sum over all I of kixi minus L, this is going to be greater than or equal to 0 when lambda is greater than 0 and x is not feasible. That is, this constraint is not satisfied by this solution x. So if x is not feasible, this quantity lambda times the sum of kixi minus L goes greater than or equal to 0. In that way, this term lambda times the sum of the kixi minus L is penalizing a violation of this constraint. When the constraint is violated, there's a positive penalty associated with it. The Lagrangian relaxation is going to leverage this idea of penalizing a violation in a constraint. So now let's write the Lagrangian relaxation and verify that it is in fact a relaxation. We'll denote the objective function of our Lagrangian relaxation by z superscript r. And whenever we write a Lagrangian relaxation, the parameter lambda has to stay fixed, that is, it's a constant. So this objective function is a function of lambda. To write the objective function of a relaxation, we take the objective function of our original program, cixi, and now we add in a term that's penalizing the violation of the constraints. And as we write lambda times the sum over all I of kixi minus L. The constraints of our program are going to remain the same. We dropped one constraint and keep all the others. In this case, all the others are the sum of the aij xi is less than or equal to bj. And also our xi still remain in the same lattice set. That is, these are the natural numbers to the n. And now, for the future, we'll denote these feasible region by p. Now we have a different feasible region. And we'll denote our objective function by g of x. This is the Lagrangian relaxation, and now we'd like to verify that it is in fact a relaxation of our original integer program. To show that it's a relaxation, first we'll just observe that the feasible points in x are a subset of the feasible points in p. So our relaxation has expanded the feasible region. This is easy to verify. The harder thing to verify is that for all x in our original feasible region x, our original function f of x is going to be less than or equal to g of x. But we can convince ourselves that this is true. If we have a feasible solution in our original problem, a feasible solution to our original integer program, this remains a feasible solution to our new problem over here. And the value of this new problem is going to contain the objective function value of our original problem. And then, if our constraint is satisfied, this term, negative lambda times the sum of kixi minus L, can only be positive. So for a feasible point, this maximum can only increase. This is how we're going to verify that for all x in our feasible region, f of x is less than or equal to g of x. There's going to be some funniness for how these functions behave outside of our feasible region, that is in points in P, but we'll get to that in the next slide. For now, we should just verify that this is in fact a relaxation. So now we can consider the Lagrangian relaxation from a more geometric perspective. Here we have the two sets drawn, x and P. And what we'd like to understand is how f of x and g of x relate to each other inside of each of these regions. Keep in mind that both of these polyhedrons that I drew, the pink one and the blue one, are just outlines of the feasible points. In the Lagrangian relaxation, the feasible points are actually on the lattice. I'm just circling them with these polyhedra. First, we note that inside of this blue region, that is inside of our original feasible set x, f of x is going to be less than or equal to g of x. The intuition here is that the term that we added to our objective function penalizes a violation in the constraint. When the constraint is satisfied, this penalization term is only going to add to the maximum and so increase the function value. Inside of this other region, the story is a little bit different. In this case, we don't know if f of x is going to be less than or equal to g of x. In fact, we don't know anything at all about them. F of x is basically a question mark between g of x. For any point in this region, it could be that g of x goes below or can possibly go above f of x. But this doesn't really matter. What we care about in the relaxation is that at the optimal solution, that is zr of lambda, we get that this is at least the value of our original IP solution. And this is still going to remain true. The reason this is going to remain true is because any feasible point in our original integer program, any feasible solution, is going to achieve a value of z star. Our optimal solution is going to achieve a value of z star. And this optimal solution is going to be a feasible solution to our Lagrangian relaxation. And because f of x is less than or equal to g of x, this optimal solution, when we put it inside of the Lagrangian relaxation, is going to have a larger objective value. Since the Lagrangian relaxation is a maximization problem, the optimal solution to that relaxation can only increase. So this is the main inequality we like to use. Now, it might be a little bit of a question of how we're actually going to use this Lagrangian relaxation, specifically when we deal with all of this funny business inside of this polyhedron P, where we don't know exactly how the objective functions relate to each other. So we can outline how we're going to use the Lagrangian relaxation. But keep in mind that for now, we only need to know what a relaxation is, and that is going to be something that's useful. In the future, we'll describe exactly how to use these guys. To use this inside of an algorithm, what we generally do is we're going to formulate the Lagrangian relaxation, and then we're going to solve it. Because the relaxation is a relaxation, it should be easier to solve. Then we take this solution, the Lagrangian relaxation solution, and instead of evaluating it at x, we evaluate at f of x. Now this solution that we get from the Lagrangian relaxation is not necessarily optimal. But we do have a handle on how good this solution is by taking it and evaluating it at our initial objective function for the original IP, f of x. Of course, we shouldn't expect optimality because this is a relaxation and it's not the original integer program. So now that we have a handle on the theory of Lagrangian relaxation, let's see how we actually use this. We'll work with the problem, the multidimensional knapsack problem, which is a lot like the knapsack problem, except now we have two capacity constraints. We're trying to maximize the sum of the values in our knapsack subject to a constraint on the sizes and a constraint on the weights. That is, the sum of the weights is less than C2 and the sum of the sizes is less than C1. We're going to formulate our Lagrangian relaxation, so we've picked some constants, lambda 1 and lambda 2, to multiply to these constraints. Now we go through the mechanical procedure of writing the Lagrangian relaxation. So it's going to be the maximum of the sum over all I of VIXI our original objective. And now we add our penalization terms. We're going to subtract lambda 1 times the sum over all I of si xi minus c1, and also subtract lambda 2 times the sum over all I of wi xi minus c2. Our feasible region now is really trivial. It just says that xi's just have to be 0 and 1. Now typically after we write a Lagrangian relaxation like we just did, we can do a lot of simplifications. And that's what we're going to do here. So we're going to simplify this by first grouping the terms. We'll maximize the sum over all I. And now in front of all the xi terms, we have some particular term, which is going to be vi minus lambda 1 si minus lambda 2 wi multiplied by xi. And then we're going to add some constants, lambda 1 times c1 plus lambda 2 times c2. Our feasible region is still going to be written in this trivial way. When we group terms like this, we can start to realize what the structure is actually turning out to be. There's some constant in front of xi, this ki. And the reason this is constant is because every term inside of this expression is constant. Vi is a constant, it's an input parameter. Lambda 1 is a constant that we chose, si is input, lambda 2 is a constant, and wi is an input parameter. Also, part of this objective function is just a constant simpliciter. This doesn't even have a variable to maximize over inside of it. It's just a number. So we can effectively get rid of it inside of our maximization problem. If we do this, if we define this new term as ki, we can rewrite our original problem, our original Lagrangian relaxation, as the sum over all I of ki xi, subject to xi being in 0 or 1. Now we have the structure down in front of us, and from this it should be apparent that this is an easy problem to solve. This is an easy problem to solve because all we need to do is sort the values, sort the ki values, and include all the positive ones in our knapsack in the top. This is going to give us a Lagrangian relaxation solution. It's not necessarily going to be a feasible solution to our original knapsack problem, but that doesn't matter. All we care about is solving the Lagrangian relaxation. We'll see how to use the answers to these later. The takeaway from this is that when we take a Lagrangian relaxation, it is a mechanical procedure to get to the initial stages. But usually we'd like to simplify our Lagrangian relaxation until we get to something that's actually easy to solve, something that's useful. Before we leave Lagrangian relaxation, I'm going to introduce the Lagrangian dual. So in the Lagrangian relaxation, our lambda is some constant. And then we write the Lagrangian dual, and this is going to be true as long as this constant is greater than or equal to 0, as long as I choose any constant. So we can ask ourselves, well, why don't we just choose the best possible constant? And in some sense, the best possible constant is going to be the constants that are going to penalize the constraints in just the right way. That's the idea behind the Lagrangian dual. So the Lagrangian dual, instead of fixing the value of all of the lambdas, what we're going to do is we're going to take the minimum value of all of the lambdas that are greater than or equal to 0, and then solve on the inside our original maximization problem. Ki xi minus L. And we're still subject to the same constraints. The sum over all I of aij, xi is less than or equal to bj. And xi is going to be in our lattice. So here the thing that's changed is we've taken a minimum over all lambdas greater than or equal to 0. So we're solving the Lagrangian dual for every possible value of lambda, and then we're going to choose the lambdas that are going to minimize this value. Since we have that the z of Lagrangian dual, the z of our relaxation for all lambdas, is greater than or equal to z star for all lambda greater than or equal to 0, in our Lagrangian dual, we know that this is still going to remain an upper bound. If this inequality is true for all lambdas and we minimize over the lambdas, we're still going to get that this inequality is true. The Lagrangian dual is going to be very powerful, but we're going to run a whole series of lectures on using this and seeing exactly what the structure of the Lagrangian dual is. For now, we should just keep it in mind that we can potentially do this thing that integrates out the lambda by taking a min over all the lambdas.